When looking at a live database, you don't see a neat summary. You see thousands of rows of raw data pouring in every second. Your job is to cut through that noise. We need to isolate specific withdrawals, track activity for a single month, and combine customer profiles with their transaction history. These two tables are our starting point. The account table holds customer names and addresses, while the transact table tracks deposits, withdrawals, and dates. We are going to write 4 specific SQL queries to pull exactly what we need from these tables and build a polished financial summary report. If you want to code along, set up your MySQL environment with these 2 tables now. Storing data is a basic function. Extracting the right data at the right time is how you actually analyze a business's financial health. Let's write the first query. Step 1 is isolating specific transactions. Right now, we only care about money leaving the bank, which means we need to filter for withdraw events. We use the where clause to do this. By writing select asterisk from transact where type equals withdraw, we tell the match that exact text. Notice the single quotes around the word withdraw. In SQL, text strings must be enclosed in quotes. If you forget them, or if your database is case sensitive and you type a lowercase w, the query will fail. The result is a clean output showing only 2 records, T001 and T003. We've removed the deposits entirely. Step 2 requires a different kind of filter. We need to find all transactions that occurred specifically in May of 2017. The dates are stored in a full year, month, day format, so an exact text match won't work easily. Instead, we use the like clause paired with wildcards. A wildcard is a special character that substitutes for any other character or string of characters in a search. In MySQL, the % is a wildcard that represents any number of characters. By writing like % minus 05 minus %, we are telling the database to look for a dash, 05 dash, and to ignore whatever year comes before it or whatever day comes after it. This query isolates a single record, account 102, which made a $2,000 withdrawal on May 12th. Filtering and pattern matching allow us to strip away irrelevant noise early on. Once we isolate the exact rows we need, we can start combining them with other tables. We have a structural problem. If we want to know exactly who made a transaction, we can't look in the transact table. The transaction amounts are there, but the customer names are locked over in the account table. Step 3 is the equijoin. An equijoin is a SQL operation that compares a common column between 2 tables and returns the rows where those values match. Looking at both tables, they share an account number column labeled ANO. We can use this shared column to link the tables and find people whose transactions were $3,000 or less. If you just tell SQL to select ANO, the system gets confused. It doesn't know whether to pull the ANO from the account table or the transact table. This triggers an ambiguous column error. We fix this using table aliases. By assigning the letter A to the account table and T to the transact table in our from clause, we can write A.ANO equals T.ANO. These aliases dictate exactly which table to pull the shared data from. With the equijoin clearly defined, the query runs successfully. We get a single combined table displaying the account number, customer name, and the specific transaction amount. Linking datasets through common columns is how we turn isolated lists into a complete record of customer behavior. Step 4 moves us past individual rows. Now we want to summarize the data across multiple transactions. Our final objective is to find the total number of transactions and the minimum transaction amount, but only for accounts that have completed more than one transaction. To do this, we use the group by clause. This command clusters identical account numbers together, turning multiple individual rows into distinct logical buckets for each customer. Once the rows are grouped, we apply aggregation functions. Count asterisk counts the total number of rows within each bucket, and min amount calculates the smallest financial value in that same bucket. When beginners try to filter this result to show only accounts with more than one transaction, they often try to use the where clause, writing where count asterisk greater than 1. The query immediately fails. In SQL, the where clause can only filter raw individual rows before they are grouped. The having clause is specifically designed to filter the aggregates after the grouping is complete. By writing having count asterisk greater than 1, the query succeeds. The output displays the aggregated metrics for account 102 and account 103, as they are the only two with multiple records in the table. We have taken dozens of microscopic transactional actions and condensed them into macroscopic strategic metrics. We started with a chaotic scroll of numbers. Now we have 4 distinct queries that filter text, match date patterns, join tables, and aggregate metrics. You've built a functional, multi-level financial reporting tool using just a few lines of logic. I challenge you to modify this script. Go back to our equi-join query and change the threshold to find transactions greater than $10,000 instead of less than $3,000. Then, in our final query, try swapping the min function for a sum function. Watch how the output changes from showing the smallest transaction to revealing the total capital moving through each account. Mastering these commands provides a precise framework for interrogating a database and surfacing the functional metrics a business needs to operate.